So here we're going to take a few minutes and talk about, let me grab my pen, and talk about pH. Right, so pH is something that we've all kind of heard of. We've kind of danced around it before, but very few people have really talked about it in depth and from a chemistry perspective. So what the idea of pH is that it's a scale, right? You talk about a pH scale, and it helps us quantify how acidic, or on the opposite end, basic something might be. The scale really runs from the range of about 0 to 14, and all of your acids and bases are going to fit somewhere along that scale. So down below we have a quick example of a pH scale here, and I think the first thing that kind of jumps out is that you've got your acids and you've got your bases, and these arrows should not be overlooked, right? So your acids are basically going to be anything that has a pH that is less than 7. And then on your other side, bases will have a pH of greater than 7. So any acid or a basic thing will fit into kind of those two spots. And then right smack in the middle is neutral. Typically, neutral gets thought of as water. Are there other things that are neutral? Sure. But water is kind of the big one, especially because we're talking about solutions here. I guess, like a salt water solution, NaCl, typically does have can have a pH of around 7, but just a little bit of 7, but just a little bit of acid or a little bit of base mixed in there will mess it up. It's actually kind of a neat thing. This is a little bit of a side note, but if you talk about salt water or NaCl solution, so NaCl aqueous, yes, that should have a pH of 7 because what is it? It's NaCl and it's water. But a typical problem in the environment nowadays is all of our emissions from our factories and things like that have gone up into the sky, and when they are coming down as rain, it's coming down slightly acidic, and you talk about acid rain. So even though like salt water or pond water should technically have a pH of around 7, it usually ends up being slightly acidic with a pH of slightly less than 7 because of all that pollution. So it's a little bit of a rabbit trail there, but let's get back to our pH scale. So it's a scale from 0 to 14, right? Anything less than 7 is an acid, anything greater than 7 is a base. One thing that we talk about a lot when you're talking about pH is you talk about indicators, which is what this section, this colored section at the top is, why it's colored like that. So we use things called indicators in chemistry. They're usually chemical substances themselves, that we can put into solutions and they will turn colors based on if something is an acid or a base or neutral. This scale that is actually at the top of this pH scale is from what's called the universal indicator. So universal indicator, the word universal should kind of cue you off to this, but a universal indicator will change a different color in basically every pH, which is why you see such a large spread of colors here, right? We've got dark purple, blackish almost. We've got dark red and maroon. We've got green in the middle, so on and so forth. So it's a universal indicator. There's another indicator called phenolphthalein. Let's write that out. Phenolphthalein, kind of a strange word. And phenolphthalein is an indicator that's used in titrations a lot because it turns a bright pink anytime the pH is greater than 7. So it's kind of important in its own area in chemistry. But indicators are a common thing. Another thing that's good to talk about while we're here is the effect, I'm going to erase just a little bit, is the effect of mixing acids and bases and how that changes and plays with pH. So let's say I have a vinegar solution. Right, so vinegar is acetic acid, so that is going to be acetic acid, sorry. So vinegar is acetic acid, which means its pH is going to be less than 7. It's actually somewhere in the ballpark of 3. So what's kind of neat, kind of in that area, what's kind of neat about acids and bases is that this pH scale is not fixed, so we can change the pH of something by adding bases. And that idea really goes back to when you mix an acid and a base, it always produces, or almost always produces, water and a salt. So it goes from things that have pH of not 7 to two things that are both neutral. So it's kind of neat. If I take vinegar, right, and say I add to it a whole bunch of base, the pH is going to scooch further towards the neutral part of the scale, because when my acids and my bases react, we produce water and salt, which both have pHs of 7. Right? So if I add a little bit of vinegar, maybe I'll jump over to 4. Add a little bit more, maybe I'll jump over to 5 or to 6. What's kind of cool though is that if I keep adding base to my vinegar, we'll be moving that way. If I keep adding base though, eventually I'll neutralize out my vinegar. And if I add base beyond that, all of a sudden it will turn into a basic solution. I'll go 8, 9, 10, 11, 12, and so on and so forth. So there's kind of an interplay there between acids and bases. They're kind of the opposite of each other in that they can fluctuate each other's pH, right? You can add base to an acid to increase its pH, and you can add acid to a base to decrease its pH. You can add enough that it goes all the way to the other side, or you can add just a little bit just to fluctuate it a little bit. So it's a big concept in chemistry, is that you can kind of play, it's a lot of chemistry that you can do once you have this acid-base idea.